Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to write force equations for objects undergoing circular motion. So I've got this picture here, and there's kind of a story that goes with this. One day last year, a couple weeks after I bought this nice brand new Fujitsu computer that I really like, it's actually the computer I use for making most of these videos, I was driving home one day and I noticed that it wasn't sitting next to me, and I said to myself, I wonder where I left that computer. Well, a few seconds later, I went around a curve and I looked in my rear view mirror and I saw that computer crashing on the road and busting into a bunch of pieces. And then I realized where I had left it. So this problem is going to be about that computer. And what we're going to do is, I'm just going to make up some values here, but we're going to try to estimate the frictional coefficient between that computer and the top of the car, based on just some guessed values here. So this picture that we're looking at, here's my car going around some sort of curve, and here's my computer sitting at the top that I didn't know about at the time. And what we're going to do is we're going to draw a free body from right behind the car, a viewpoint maybe looking like this. So here's like an eyeball here, and looking at the computer too. This isn't about the car, this is about the computer. So a free body diagram of that computer, looking right behind the car. I've got a nice little picture here. We would have the gravitational force down, mg. Okay. This is the bottom of the computer that was in contact with the car. That creates what we would call a normal force, which would be vertical. Again, this same force would act down on the car. Now, here's the thing about circular motion. At the instant shown, the velocity vector of the computer would be the same as the car, and it's in this direction. So I'm going to put a blue vector, v. If the net force on that computer were 0, that velocity would stay constant, and that computer would follow this path. Now, the computer, at least for a while, was undergoing circular motion. That velocity vector, at least before it came off the car, that velocity vector wasn't constant, it was changing in direction. The acceleration direction, I'm going to draw this in red, at the instant shown is this way, and that's a centripetal acceleration. Now, I was going around that corner at roughly constant speed, so at this point we don't have a tangential acceleration, only a centripetal. Now, when you have an acceleration vector like this, there's got to be a force responsible for it. And that force is the frictional force between the computer and the top of the car. From this picture, that has to be in the same direction as the centripetal acceleration, so that points left. Now, that's pretty well it. That's a complete free body for the car, or I'm sorry, for the computer sitting on top of the car. Now it's just a matter of writing force equations. First, the computer isn't accelerating up or down, so the sum of all forces in what I'm going to call the y direction is equal to 0, calling this way the positive y direction. Pretty short, easy equation, right? We get the normal minus mg is equal to 0. So the normal force is equal to mg, the weight of the computer in this example. Next force equation, the sum of all forces in the x direction is equal to mass times acceleration. Again, Newton's second law in general is force equals ma. This one was a 0 because there was no acceleration in the vertical direction. Here, however, there's an acceleration towards the center of curvature. In this picture, that's in the same direction as this. That's this way. So that's what I'm calling now the x direction. And I'm following my standard rule of thumb. Identify the acceleration direction, call that positive. So we look at our free body of the computer, and the frictional force is the only force in that direction, equals mass times acceleration. So because that's a centripetal acceleration, is equal to v squared over r. So, free body diagram, pair of Newton's second law equations. Now, the next thing to do here is we're going to talk about this, frictional forces. So, quick little reminder, your frictional force, let me back up. Surfaces in contact have two frictional coefficients. You have what's called a coefficient of static friction and a coefficient of kinetic friction. You use the coefficient of static friction to find the maximum possible frictional force. and that's what we're going to use here. Our maximum possible frictional force is equal to our coefficient of static friction times the normal. So I'm going to go ahead and insert this for our frictional force. In fact, I guess I'll just get rid of this. Alright, so we have coefficient of static friction times our normal for our frictional force equals mv squared over r. This would be true right as that book broke free from the surface of the car and starts, oddly enough, what happened was the car accelerated out from underneath it and that computer tended to go more straight. So our normal force we can get from here. So now we have coefficient of static friction times mg equals mv squared over r. And you'll notice here our mass divides out. So we have a coefficient of static friction times g equals v squared over r. Now at this point you're probably wondering, well, I don't see any values for these. All I can do is kind of make up values. This happened a year or so ago, but I'm just going to make up some numbers and then leave it as an exercise to the reader to calculate a frictional coefficient that goes with this. I don't know. Let's just say it was a 75 meter radius curve and I was traveling at 20 meters per second. I'm just completely making up values. The rest of this problem will be just putting in numerical values here, here, and solving for the mu sub s. Our gravitational acceleration at the surface of the Earth is 9.8 meter per second. That's not important enough for me to worry about right now to even do. I don't have a calculator handy anyway. The important thing is recognizing that the acceleration of the computer was inward towards the center of curvature. 2, recognizing that the computer was undergoing centripetal acceleration before it slid off the car. 3, drawing a free body of this computer from either a behind the computer or in front of the computer would have been just fine, and then here's what that free body would look like. 4, how to write your Newton's second law equations from the free body. And by the way, in this example here, the frictional force was the centripetal force. So the rest of this is just algebra. So I hope that this video demonstrates how to analyze circular motion using free bodies and Newton's second law equations. Have a great day.